Hey everybody, Sam here. We've got some great news to share and also a favor to ask. We're in the running for this year's People's Choice Podcast Awards in both the People's Choice and Technology categories, and we would really appreciate your support. To nominate us, you'll just head over to twimlai.com/nominate, where we've linked to and embedded the nomination form from the award site. There, you'll need to input your information and create a listener nomination account. Once you get to the ballot, just find and select This Week in Machine Learning and AI on the nomination list for both the Adam Curry People's Choice Award and the This Week in Tech Technology category. As you know, we really appreciate each listener and would love to share in this accomplishment with you. Remember, that URL is twimlai.com/nominate. Feel free to hit pause and take a moment to nominate us now. Hello and welcome to another episode of TWIML Talk, the podcast where I interview interesting people doing interesting things in machine learning and artificial intelligence. I'm your host, Sam Charrington. Consider this your final update for tomorrow's TWIML online meetup. On Tuesday, July 17th at 5 p.m. Pacific Time, Nick Teague will lead a discussion on the paper Quantum Machine Learning by Jacob Biamonte and his co-authors, which discusses how to devise and implement concrete quantum software for machine learning tasks. Visit twimlai.com/meetup for more details or to sign up. In this episode, I'm joined by Amir Zamir, postdoctoral researcher at both Stanford and UC Berkeley. Amir joins us fresh off of winning the 2018 CVPR Best Paper Award for co-authoring Taskonomy, Disentangling Task Transfer Learning. In this work, Amir and his co-authors explore the relationships between different types of visual tasks and use this structure to better understand the types of transfer learning that will be most effective for each, resulting in what they call a computational taxonomic map for task transfer learning. In our conversation, Amir and I discussed the nature and consequences of the relationships that he and his team discovered and how they can be used to build more effective visual systems with machine learning. Along the way, Amir provides a ton of great examples and explains the various tools his team has created to illustrate these concepts. And now, on to the show. All right, everyone, I am on the line with Amir Zamir. Amir is a postdoc researcher with, get this, both Stanford and Berkeley. Amir, welcome to This Week in Machine Learning and AI.
Thank you. Thanks for having me.
Let's get started by having you tell us a little bit about your background and how you got involved in machine learning and AI and how you ended up with an appointment at both Stanford and Berkeley.
Sure. Regarding my background, I was always interested in math and physics, especially in middle school and high school. That turned into interest in signal processing when I was in college. And one of the sensors that produce a signal from the world is camera. And that's the way I essentially got exposed to visual perception and making sense of this raw sensory data, like an image that we use on a daily basis. But getting the computers to make sense of that struck me as a really fascinating problem. It appeared both simple and nearly impossible at the same time. And that was really the point that made it fascinating and challenging. As a human, when you see an object, see a dog, when you walk, see something new, or you're at a particular location and you know where you are, you can recognize objects, you can just do this without any particular difficulty. And you can do it at actually a very young age. Like children, they're just a few months old, they can solve pretty much all of these problems. So it appeared like a very simple problem that anyone can do. But when I was looking at the machinery that we had back then to get computers to do some of these very basic things, like just detect an object or tell apart whether like two things that you're looking at is the same thing or not, basically match them. It looked far from solved. And that's where it all started for me.
Wow, and we've certainly come a long way in that dimension. I remember taking a DSP class in grad school. The prof was focused on computer vision, a guy named Agelos Katsagalos at Northwestern, and the way we approach that problem now is very different.
Right. Yeah, that is indeed correct. A lot more machine learning is in play than when I was in early years of college. That's actually interesting. A few years ago, just let's say, 5 or 7 years ago, we were doing a lot more handcrafting or solutions to rely on our intuition to solve some of these problems, like what makes an object, what makes a dog, and we would extract some certain low-level features, and then we would come up with heuristics for putting together some representation of that, and then maybe there would be some machine learning layer sitting on top and classifying them. We have certainly the scene has changed a lot since then, for better. Judging by the metrics that we have in the field, we are doing a lot better than what we were doing back then. It doesn't mean the problem is nearly solved. I have to admit that I have a better understanding of the complexity of this problem now than a few years ago, and I see as much unsolved problems that I could see back then. But the progress made is something that can't be denied.
When you look at the problem space and you see, as you said, as many unsolved problems now as then, are the problems the same in scope or texture, or do you have a mental model for taxonomizing the problems and how the problems have shifted over time?
Yeah, that's a good point. The problems have shifted. Not trying to not get into too much details of it. I would basically abstract it this way: is that a few years ago we were defining a problem in terms of some input and output. Let's say input was an image and the output was like the objects that you're interested in, or the input was an image and the output was, let's say, some 3D properties of the scene, let's say layout of the scene, or surface of the normals of the surfaces in it, and so on. So back then, what we were mostly struggling with was that we just couldn't solve this problem good enough. Like object detection is a very good example. ImageNet, say, looking at 2010, ImageNet is a challenge, is a pretty complex challenge. There are like 1 million images and 1,000 objects, object categories. They need to classify these images into those or detect them. So people were trying really hard. It was getting quite a bit of attention and energy. So it's not like people weren't trying hard enough. A good part of the community was trying. But in the end, when you would look at the failure cases, they would look very simple. You would detect a car in the sky, or you would hallucinate certain animals just in the middle of the wall, and so on. We knew why they were happening, but didn't know how to fix them. So since then, the horizon of the problem have shifted. I think we have basically pushed the umbrella a little higher. And so at this point, after namely when deep learning wave happened in computer vision back in 2012, 2013, with Alex Krzyzewski et al. Paper on ImageNet, which significantly improved the performance. So since then, there is this summary that more or less a lot of people have in mind, is that if you're interested in solving a particular problem, like problem X, you collect a large amount of data for it, and you train a big ComNet, these neural networks. That will probably give you satisfactory results. It's a matter of throwing in more compute and throwing in more data if you want to improve, and that's the only problem that you care about. So I think we have grown out of that local minima that we are just really interested in one problem. We are trying to do anything we can to solve it, but we still were facing difficult issues. Right now, I think a lot of these things have changed. Like I said, for a large part of the problems, if you can really clearly define the problem that you're interested in terms of input and output, having a lot of compute, doing some search over different architectures that you can employ. And if you can afford having a large data set for it, you can get a reasonable accuracy, probably something that would be useful to even turn into a product for users. And we have seen examples of that, like face detection or recognition, and certain filters that you use on Facebook and YouTube and so on. They're using these tools. I think the horizon now has shifted towards basically, okay, well, if we want to solve these problems, but if we don't have enough data for it, or we don't want to use an unreasonable amount of compute for it, or a little bit more futuristic is that, like, why are we solving the problems that we are trying to solve? Like, what is the genuine basis for some of these problems that we have defined, say objects or normals or depth and so on and so forth, because these are purely based on human intuition. And ultimately, I think integration of a visual perception module into a bigger system like a robotics system. These are the things that we have started to basically approach, and I think these will be the biggest problems in a few years to come to be tackled by the research community.
You mentioned tackling this challenge of solving these kinds of problems with less data, and one of the solutions that the research community has come up with there is transfer learning. And that's the subject, or at least the context, of a recent paper that you were a co-author on that won the Best Paper Award at the recent CVPR conference. Can you tell us about that paper?
Yeah, sure. So that paper is called Taskonomy. It's actually, we call it Taskonomy because it's task taxonomy. It gives you a taxonomical transfer policy over different perceptual tasks. So the idea there is that, let me give you actually a non-perceptual example. Let's say if you want to learn how to play a board game, the first board game that you learn takes time because you're just learning the very basics. You realize that, well, board games are usually composed of a board, some surface, and on which there sit some pieces probably, and these pieces have some categories, like turn into different colors, and there's usually some flow. You want to move some pieces from one part to another. So none of these have to be 100% true for all games, but more or less there's some structure there. And the first time that you're exposed to such a thing, you are just learning everything from scratch. So it takes more time. Now, imagine you have learned how to play 20 board games. The next one will become a lot faster because you have understood the basic structure of the game. Also, even some of the moves that you have learned in the previous games will be useful for the next one that you're going to play. So essentially, you're transferring some useful knowledge that you learned before. You're distilling it and applying it towards a new problem that you're facing. And that process of successfully transferring and not having to start from complete scratch is what makes you faster. And that generally applies in a broad set of domains. Games was just one example, but literally everything that we do as only working example of intelligence as humans, or generally the brain, we leverage this transfer principle a lot. What makes something transferable or not? Those are basically very open questions there. But leveraging this concept has a lot of benefits. And taskonomy is that for perception. So we define a lot of problems in computer vision that are deemed useful, and the research community has been trying to solve them for a long time. Examples of that, like I said, the most popular ones are like object detection, or 3D properties of the scene like depth, normals, curvature, estimating the lighting of the scene, or what is the layout of the room that you're at, or some other ones like self-localization. If you're in a room and you're moving, or let's say you're just watching a YouTube video and the camera is moving, you can predict how the camera is moving. You can draw a trajectory of that. So the problem of like localization or camera pose estimation, if you want to put it in vision terms. So these are problems that we generally solve. And pretty much all the papers that come out in computer vision community, the majority of them are addressing one of these problems. They focus on one problem and try to come up with better and better and better machinery to improve the performance in every single one of those problems. So, but these problems are related to each other. They're not independent, just like the board games are related to each other. The relation might not be trivial, but some relationship exists. The example I gave actually when I was at CVPR, giving the talk was layout of the room and the objects that are in there. So when you're in a room and you just open your eyes and see you're in a certain room, in a conference room or anything, you have an understanding of the 3D layout, where the floor is, where the ceiling is, where the walls are. And that gives you a pretty strong prior about where the objects would be. You would never look for the chairs on the ceiling. You would just look for them somewhere close to the ground plane, because they need to receive support from the ground to stay. Or you would look for lights actually close to the ceiling, because that's just the way the world works. So that the spatial prior that you get from problem A, in this case was layout of the room, was very useful for problem B, which in this case is object detection. So the relationship between problems clearly exists. And if we can develop some machinery to make use of these relationships, to solve the new problems that you face without having to start from scratch, by borrowing those things that you have learned already and apply it towards solving a new problem, that has a lot of benefits. And taxonomy is a method for actually trying to do that. The challenges there, obviously, is that how you want to do this. But the premise of it is that let's view the tasks that we solve in computer vision in concert. Let's recognize that they are related to each other, and now solve them in concert rather than starting from scratch and individually approaching them, which is one of the biggest reasons that, in general, machine learning and neural network systems that are working today, they are very data hungry. They require a massive amount of data to start producing the good results. And using this like transfer learning approaches is a potential remedy to that problem.
Some of what you're describing reminds me of something I wrote about in my newsletter a couple of months ago. I think there was a data set that was published called, I think, Home 3D. And the broader project was to provide a data set. It was part of a challenge, I believe, that was to try to come up with an agent or a model for determining what room you're in based on 3D images. Is this a related project to some of the work that you're doing? Do you know that lab?
Right. Yeah. I'm aware of Home 3D. There are like alternative efforts also similar to that. So in general, these are all related in the sense that we are generally moving from data sets to environments in computer vision. So the notion of a data set is something that, in image data sets, like ImageNet, again, is the most popular example probably, is that we collect a set of images and we put some meta information on it. For instance, somebody sits down and annotates that these are the objects that you see in there, or this is the layout of the room, or these are the 3D normals of the surfaces, and so on and so forth. The main point about data sets is that they are static. So they can't change. You cannot say that, okay, I'm looking at this image, let me just reposition myself with respect to the object to get a different perspective. That's just fundamentally not possible, because these are passive and they're offline. They're recorded once and that's it. A large part of perception is related to agents that need to be ultimately active in the world, like robots. We need to create a home for them to learn in this particular way, because that's the way they're going to be operating. So the trend of moving from data sets to environments is mostly motivated by this desire. Now, how this is related to transfer learning and taskonomy in general, the relationship is that, in my opinion, ultimately, we need to throw an agent in an environment and ask it to do something for us, something useful, that is not perceptual. Like, let's say if I have a robot at home that I want to ask it to bring me a can of soda. Perception is something that is in service to that downstream goal, which is just fetch a can of soda from the fridge and bring it to my desk. Now, what problems that entails, like what set of perceptual problem bring a can of soda entails, is not a trivial question, despite what it sounds like. We cannot really easily make a list of perception problems we need to solve to enable an agent to do some of these tasks. In that sense, then we have to view the problems that we want to solve. Let me actually make that a little more understandable. Let's say a can of soda. The agent needs to obviously know where it is, so it needs to self-localize. When it's moving, it needs to understand how it moved. So the one step that it took, how it changed, in what direction it went. On the way, of course, it shouldn't hit like obstacles. You need to realize that when you're in a room, the way to get out of the room and go to the kitchen is through the door. So you need to do certain semantic understanding. And when it sees a can of soda, you need to recognize it and have enough skills in terms of control to grasp it and bring it on so far. So what are the perceptual problems? I just made a list, but is that complete? No. A lot of things can actually go wrong if you think a little bit more about it. And ultimately, also, we don't want to have robotic agents that are single task. We don't want to have an agent that just can bring a can of soda for you, but cannot make coffee, perhaps, or bring a cup of coffee, or fetch, clothes from the washing machine. Ultimately, the set of perception problems we need to solve to put it on an autonomous agent to do something useful for us is a non-trivial problem to create a list of them, and the list is going to be long. That's at least what we can say now. Now, if you have a long list of problems, even if you can make that list, first of all, if you want to individually solve them on the fly, you will burn a lot of compute, which is unnecessary because, like I said, these problems have relationships and certain redundancies. So you should view these tasks in concert rather than individual concepts living in isolation. And also, it's not even that feasible, in my opinion, to just collect a certain amount of data for every single one of those problems and assume that you can just solve them to perfection individually and then integrate them in an agent. Again, there has to be some connection between these and transfer, like so. So there should be some highways of information between different tasks, and that should be very fluid, built into the system. So the relation that comes from like taskonomy and transfer learning in general and those like environments is in that sense that makes the problem a little more exposed, that we really need to view problems in concert. What we are really dealing with is a set of tasks, not individual tasks. And there's no escape from using the redundancies and like regularities within this set of tasks to make what we are trying to do feasible.
I think a lot of people listening to this podcast will be familiar with the concept of transfer learning in the sense of, for example, object recognition. You train a neural network on lots of images based on, say, ImageNet, and then you use that model and maybe fine-tune it for some other data set. Are you using transfer learning in the sense of language, or is there some commonality in the technical approach that you're taking between, task transfer learning and the type of transfer learning that we think of in the object detection sense?
Right. Actually, the object detection example is great. What we are doing is actually similar to that.
Okay.
A lot more similar to that than language. So the object detection approach that you mentioned is actually pretty interesting and pretty useful. Like you said, for a long time, the most established way of reducing the need to label data was that we have one great data set, ImageNet, and we have models that are trained on it to do object detection. People train a model on that, and then they usually get that network and then fine-tune it for another task, which is not object detection, something else, but they have way less data for it. They essentially use the ImageNet as a good initialization for solving the other problem that they're interested in. So what we did in taxonomy is actually something similar to that, but with a lot more structure and a bigger scope. So let me pose this as a question: is that why object detection, a system developed for object detection, should be useful for solving another task. Why should be the case? I mean, let's say the other task could be scene classification, right? You want to know whether you're in an office or in a living room or in a library, etc., etc. Why a model trained for object detection should be useful for that purpose? I mean, it makes sense, right? Because usually the objects that you see in a scene very well correlate with the category of the scene. If you're in a living room, you see a lot of couches. You might see a TV. If you're in an office, you usually see conference tables and chairs and so on. So if your system has some understanding of the objects, you would expect that knowledge to be very useful and very transferable to another problem like scene classification. So that's a successful case of transfer. Now, many of the problems that we want to solve are not that close to ImageNet or generally semantic problem. Right? Like I said, for instance, 3D understanding of a scene. It's not clear why a network that can do object detection would be useful for you to understand, let's say, normals of the surfaces in a scene, or just depth. Depth is actually quite important problem because, for instance, at minimum, it can allow an agent to not run into things. You need to understand how far you are from the thing that you're in front of you. So that's an important problem. But the relation between that and something like object detection is not clear. And, the research community has also found experimentally that ImageNet features transfer to different problems with different success. So if the problem somehow has a reason to be related to object detection, usually transfer is more successful, and there are failure cases too. Certain problems that the ImageNet just does not transfer well to it. So this is actually the premise where taxonomy builds on. We are recognizing that some problems are more related to other problems. And there is some structure in this space. Let's say if I make a list of all tasks that you can think about like perceptually solve, this will be some 3D tasks and some low-level 2D tasks, like what are the edges and so on, and some semantic tasks, like what are the objects, what are the category of the scene that you're looking at. A lot of things that are not based on image content, but also returning information about the agent, like I said, self-localizing the agent and so on. So there are some modes of tasks. There's some cluster of tasks. So there's some structure there. So if you want to successfully transfer from the knowledge that you have right now to solving a novel problem, you need to understand this structure. You need to understand that if your new problem that you're facing is something related to 3D, you probably should transfer from the other 3D tasks as compared to semantic. If the problem that you're facing is something related to semantic, sure, something similar to object detection is a better idea. But doing all this completely automatically without having a human in the loop that sits there and says, oh, this problem sounds 3D, so let me transfer from other 3D tasks. And this problem sounds semantic, let me transfer from other semantic tasks. So having a machinery that in a fully computational way discovers this structure of this space. And now when it faces a new problem, it can say that I want to transfer from those set of tasks, not the other set of tasks, is basically what taxonomy does. So we are not really forced anymore to transfer from ImageNet to any problem that we face. There's a system now in place that it can advise you on where you should transfer from. And the good thing is that we can evaluate that. So in all of our experiments that we have. Actually, there are plenty of live demos on our website too, taskonomy.vision. If you visit there, you can actually play around a lot with the tools that are there. You'll see that as a baseline, we also show what result you would get if you transfer from ImageNet rather than this kind of adaptive transfer policies. And you'll see that the adaptive transfer policies actually outperform the ImageNet counterpart significantly. That essentially tells us the concept of making use of the structure among tasks and adaptively deciding where you should transfer from and how you should transfer is something that is useful. And we were also able to successfully extract that structure and have a fully computational method for enforcing that without having a human in the loop to tell us about this, let's say intuitive relationship between problems.
I had several ideas starting to form about what exactly Taskonomy was trying to do throughout this first part of our conversation. And I think it started to firm up right there at the end. One of the ideas earlier on was some system that was, I guess you could think of it as kind of some ensemble of a bunch of different types of networks trained to do different types of tasks. And some, what you were trying to do with Taskonomy was, that ensembling or that meta decision layer. It doesn't sound like that's it, but, maybe you can comment on that. It sounds more like what you've developed is, again, grossly simplifying, some kind of heuristic or decisioning algorithm that if you've got these pre-trained models, that it can, the system knows about some number, some catalog of pre-trained models and what their capabilities are, and it can maybe take a look at your problem and your data and tells you which of those models might work best. I feel like neither of these gets to exactly what you're doing, but they're kind of, maybe you can use those to help me get there.
Yeah, exactly. So I can explain a little bit more details. Let's say, essentially, the tasks that we solve in computer vision are an abstraction. You have a set of pixels, you want to read something abstract out of it. This abstract reading sometimes is an object, sometimes it's 3D properties, sometimes it's something else, et cetera, et cetera. So that's what we call a task here. So again, like I said, popular examples of that is object detection and so on. So we create a dictionary of these tasks. We have 26 of them in our dictionary. We define that dictionary ourselves. Now, we have a data set that each image, there's 4 million images in it. These are real images. They're not synthetic. So each of these 4 million images that we have our data set has annotations for every single one of those 26 tasks that we have there. So we can afford training a really good neural network to solve every single one of those 26 tasks. So we call them task-specific networks. So there's one network that is completely specialized in solving one of these problems very well, down to perfection nearly, and not care about any other problems. Now, we get the internal representation of these task-specific networks, and we try to evaluate if we can reproduce the results of another task using the internal representation of one of these tasks. Essentially, we are trying to understand that whether the information for solving another task is contained in this representation that was trained for another problem, but can possibly include the information, right?
So for example, something along the lines of looking at semantic distances between activations at different layers in the network, or?
Right. So the machinery for that quantification is, again, another small neural net. But like, to give you an example of a task, let's say the example I gave you earlier is that layout of the scene and objects, or normals of the surfaces, and say 3D curvature, so 3D properties of the scene. So let's say if you want to evaluate whether the task of surface normal includes the information for solving 3D properties of an object, like curvature, how the shape of it looks like, or layout of the scene. Let me just do layout of the scene is probably more intuitive. So we get the network that was trained for surface normal estimation. We get the internal representation of that, like one of these layers of neural nets in this big network, and we train a very small neural net that we call a readout function to read layout of the scene from the representation of the network that was only developed for surface normal estimation. So we train it using a small amount of data, just a couple of thousand images, that train does like little readout function, and then we evaluate it, whether it was successful or not. So if this very small neural net trained with a very limited amount of data, 2,000 images, was able to successfully extract the layout of the scene from the internal representation of a network that was trained for normal estimation, we call them very closely related tasks. We create a complete graph and put the edge weight representing going from normals to layout of the scene, give it a very large weight. And if it wasn't successful, we would give it a small weight. And we do this evaluation for all pairwise sets of tasks. And that gives us that complete graph. That gives us tells us how every pair of problems would be related to each other.
And just to calibrate on that one example you used, surface normal estimation is basically you've got an image and you're trying to calculate a vector that's perpendicular to the surface at each pixel in the image.
Correct. Exactly.
Right? Okay.
Exactly. Yeah, it's a 3D vector, so it's the gradients of say edges. It could be confusing in that sense. You can think of it as you're an image, you're looking at an image. You click on a point, and it gives you the normals of the surface with respect to you. Is this surface that this pixel is laid on? Is it like facing you? Is it facing different direction? What would be the 3D angle of that? Yeah.
You calculate these pairwise relationships, and that is the objective to tell you through this research the general relationships between these tasks, or is it specific to a given data set?
Right. These are not too specific to a data set. Of course, everything that we do is data dependent because it's a fully computational method, and whatever we extract is from the data set that we have. But so we have spent a lot of effort in making sure that this data doesn't suffer from too much bias. It's from indoor scenes, so obviously I would not expect the observations to generalize to say outdoor scenes or underwater imagery and so on. But as long as you what you care about, let's say indoor scenes, indoor images, so these relationships are expected to remain stable. We have actually some studies on universality of these findings. We basically fix many of these design choices, except for one, add some variance there and see whether how much of the structure that you have extracted changes or not. So we do have these studies, and in general, I can say that it's not actually very data dependent. We observed a pretty good stability in terms of high level observations. When we see that two tasks are being related in a particular form in this data set, then we go and evaluate an ImageNet or MIT Places as a scene classification data set. Usually the same trend comes out. So, and we have evaluated that experimentally. So I feel confident at this point that many of these trends that we observed there in these structures are not data specific, but they are not general also in the sense that there exist many types of relationship between tasks. And these relationships are evaluated in terms of transfer learning, essentially trying to see how much useful information one task can supply to another one. Other types of relationships also exist. Let me just give you an example, is that like computational. So maybe somebody doesn't care about reducing the need for labeled data, but they just want to say, I want to reduce the amount of computation that I can do, like the number of flops that my GPU run. So the relationship in that sense would have to be measured in terms of how much compute you can save. These things usually correlate a lot, like supervision and compute, but in principle, you would need to measure the relationship for what you're trying to optimize and make the system more efficient. What we are trying to do is basically reduce supervision, reduce labeled data. So our metric for relationship is curated for that. If one was interested in computation, or let's say storage, you want to store say a neural net that solves a set of problems, but you don't want to just individually solve them. You want to do something like compression on top of them. You don't want to save something twice if there is something in common between them. So you would again have to measure the relationship in terms of their redundancy, in terms of the storage. So in that sense, these relationships are about supervision and transfer learning. They're not completely general, but again, correlation between these different things is a thing too. But I'm not aware of any formal study towards that.
Is it fair to say that if someone was looking at trying to build a system that performed one of these tasks and was constrained in labeled data, and so thus wanted to use transfer learning to accelerate building or to allow them to build a machine that was more data efficient, that the goal of the paper is that they should be able to look in the paper at a chart that you produce that illustrates these pairwise relationships, and essentially they'd be told what transfer learning models would be helpful for them. But
exactly,
if they had another problem, such as computational efficiency, storage efficiency, whatever, they might look at the paper as guidance and need to build out the machinery that you've built out to tell them, which of these relationships is most critical for their tasks.
Yeah, that's completely true. The second part is right. In principle, if what you want to reduce is not label data and supervision, what we have, the study that we have done serves as a guideline, but not a direct optimization of that objective in principle. Now, regarding the first part, is that it actually ends up being a little more complicated than a chart, than any fixed chart. So one thing that I actually skipped over and didn't explain in detail was that, let's say, after you find all these relationships, there are a lot of them. Just the pairwise, what we call first order relationships. There are 26 tasks in the dictionary, and these are directed graphs. So there's 26 by 25 number of relationships. So it's a huge matrix. Making sense of that is not too trivial. It's not like it ends up being a chart that can go into a handbook that you can just look up a row and say, okay, this is the way to go. So when you look at these graphs, I mean, these visuals are actually on a website and a paper, but it's hard to explain them verbally. But when you look at them, many of these relationships are weak. They are not useful, obviously, because many tasks are not well related to each other. But there are many strong ones too, and you can see pretty strong patterns. So in the end, to make this useful, we want to extract a sparse structure out of it. There's no point in having this complete graph there, because you can just reduce a lot of these and get rid of them and not lose anything in terms of performance. So formally, that becomes a subgraph selection. So that's when actually it becomes a taxonomy, that becomes a tree-like structure. Is that you want, the problem ends up being that the user says, I want to solve this problem or this set of problems, but I don't have enough data for it. But I know how to solve these problems, like these 20 other problems. And then tell me how I can solve this set of problems using those, basically from what I should transfer to these target tasks, what we call neutral problems, like targets, from what sources I should transfer to these targets. And also, let's say maybe the user doesn't have the compute to run all these networks that we have trained in parallel as source. So the user would say that I can't afford having more than 3 networks running in parallel in my computer or in my agent. So what are those 3 sources that best support solving these target tasks that I care about, and how I should go from those to these? What exactly is the transfer policy? And that's why it becomes a sparse structure and a tree structure. So when you look at the examples of this taxonomy in the paper on the website, you don't see a dense graph. It's actually rather sparse, but it's curated for this very particular question that the user has, is that I care about this set of target tasks and how I should do it. And the reason it doesn't become like a fixed chart, like I said, is that these arguments are vary case by case. The user, every user cares about a different set of targets. So they specify that in the taxonomy, the transfer policy changes according to those arguments. And actually, we have an API on our website where you can go and basically you can see a partitioning of tasks. Like, these are tasks that I know how to solve. These are tasks that I want to solve, but I don't have data for it. We call them target only, like I said. And you can just press button and it runs the optimization live right there, and it puts the transfer policy in front of you. So it's not, basically, since there are many arguments in play, it doesn't end up being a fixed chart that you can just print in a PDF. But the API is the best way to see that.
Yeah, maybe I'm reading into the way you've described this too much, but it almost sounds like you're describing transfer, or a transfer policy including transfer from a given source, as a binary decision. And is that always the case? Is there, for a given task, is there only one way to transfer from ImageNet, or are there multiple ways to transfer from ImageNet, either computationally from kind of weighting that network in different ways, or transferring from different layers? It seems like there's more than one way to do it. And to what extent does your model take that into account?
Yeah, great question. So there are two basically points to be made and answer that question. First of all, one thing that we do is not, we don't commit to one task when you want to solve a target task. Like basically, there's for solving one target, you can have multiple sources. That basically corresponds to the case that where like multiple source tasks get together to solve one problem. We call them higher order transfers. That is also included in the formulation. And if you, like I said, if you run, for instance, the API, you'll see that certain targets have incoming errors from multiple sources. That basically means it found that it's useful to use more than, let's say, just ImageNet. Put ImageNet next to something else, and that was the one that produced the best results.
Sure.
So it doesn't have to commit to a certain source. Now, but just having how we quantify the how well a transfer can happen from a source to a target. Like you said, there are many different ways actually to do that, and every few months actually there's one new method that comes out. What we used actually a fixed way. Like I said, we used readout functions, but these are small neural net themselves. So at a time, and as far as I know, actually still today, they're the best performing ways of transferring from one thing to another, subject to some constraints. But yeah, in general, we commit to a single way of doing this transfer. And that time it was the best way, and then today it is still the best. I mean, they're like fine tuning and so on. You can view them as also as a way of transferring, but there are some issues with them because, let's say, if you fine tune a model for a task, you can then that becomes a copy of that source. It doesn't remain the source. So if you want to go from one source to 20 different targets, you have to create 20 different fine-tuned version of that source network, which again, storage-wise and computation-wise, becomes intractable. There's some details there, but yeah.
Awesome. Well, this is really, really interesting work. Is there anything else that you'd like to share before we close out?
I think that's it, and I think it's a very interesting topic to think about, and I believe in general we have really just scratched the surface of this problem. Ultimately, what I would expect, and at least I would like to see, is that now that we have some understanding about the space of tasks, like we're really now viewing problems, like I said, coming from a space rather than isolation. So we have a model to cover this space with less computation, less supervision, essentially bringing efficiency into the picture. So ultimately, what I'm interested in, and I would like to see, is that we can turn this into a generalist perception model that can quickly compose solutions to unknown problems that it comes its way, and possibly kind of on the fly, like in a lifelong learning manner. Now that we know the structure of this space, at least we have version 1 of it. What I would hopefully see perhaps in a few years is that we can turn these generalist perception models and maybe we can put them on autonomous agents and see them really doing perceptually complex tasks and get better through time and not require a large amount of data for every single problem that they are asked to solve for us. We'll see how it goes, but it's exciting.
Awesome. Well, Amir, thanks so much for taking the time to share this with us.
Thank you for having me.
All right, everyone, that's our show for today. For more information on Amir or any of the topics covered in this episode, head over to twimlai.com/talk/164. Don't forget to visit twimlai.com/nominate to cast your vote for us in the People's Choice Podcast Awards. As always, thanks so much for listening, and catch you next time.